I do think it's definitely the case with this type of topic when we talk about transformations and viewing. Um, at least in my experience, you can work out a lot of the math by hand, and it's not difficult math as we've talked about. But I think ultimately there's no replacement for just doing, for trying it out, for exploring, doing some of these transformations in your OpenGL code. Um, and seeing what the results are. I really I think we could cover the math until we're blue in the face. And there's some versions of a course like this that maybe cover significantly less hardware considerations, but instead really just focus on the fundamentals of computer graphics, where you could spend 7 weeks on the linear algebra and the transformations. And that can be very helpful. I think you can get a very thorough knowledge of it from that. But I still think even in that context, there's no replacement for actually going and doing. So that's my first takeaway for today. So we'll continue on with the topic that I posted on Tuesday. Basically, an application of the transformations we were talking about in the context of actually viewing a scene. Um, no matter what we talk about, give it a try. Give it a try, certainly for code you may want to write for MP3. We're getting very close to the point where the code that we talk about in class is stuff that should start to work on your hardware and just on your own, just to explore, see what the transformations are capable of, what these somewhat conceptual things mean in practice. This is where I left off at the end of Tuesday, talking about a much more of a detailed breakdown of the viewing transformation pipeline. Now, this is a subset of the overall rendering pipeline, and the degree to which we need to break it down here is more of to explore the conceptual underpinnings versus architecturally where there's an actual breakdown. A lot of what's happening here would all be taking place in one stage of our physical pipeline. It'd be in that vertex shading stage. Now we, in our desire to get things kind of working relatively up and working relatively early in the semester, we separated out the viewport transformation as a separate sort of fixed function stage, separate from the rest of this. But at least in theory, all of these steps can be done via shader code of the type that you're exploring how to compile and how to actually run in your MP3 code base there. It's a little backwards in terms of how we're covering it. We will talk about shader architecture in more detail starting next Tuesday. And I think it'll all kind of tie together in the end. It'll all ultimately make sense, if not today, by the end of the semester. And that was my goal for you. So this is a breakdown of the different substeps of the viewing transformation pipeline. And we've been kind of intentionally sort of hiding some of that detail just to get our code up and running in the hardware that we have available to us. But in practice, the truth is that there's a number of these different coordinate systems that we're translating our input objects between. We start off with our object coordinates. That's our XYZ1, and you at least should have a hand wavy idea of why we do it that way now if you look at the Tuesday lecture. That's to allow our transformations to all be composed entirely of a single matrix. So we have these three-dimensional objects still, but using this homogeneous coordinate system for it. And the idea of our input coordinates, it should be whatever coordinate system makes sense for our particular models. And the analogy I was trying to draw on Tuesday's lecture was, well, if you're trying to model a building, there's a series of XYZ values and maybe corresponding units that make sense for a building. Versus if you're separately modeling molecular structure, there's a separate set of coordinate systems that may make sense for that. Maybe we can do some application normalization, but we don't necessarily have to do that in the actual modeling of the objects themselves. Perhaps we don't normally want to compose a scene that has a molecular structure on the building, but the other example I gave was of a bird. So you may have a bird which you have some level of detail that you want to model it in, and so you'd be very concerned with that unit of measurement for those X, Y, Z coordinates, and then you have your building as a separate thing. And you may want to show in your scene a bird on that building. And so we have separate object coordinates, and as part of that so-called modeling transformation, we're going to take everything that's in its own separate object coordinates, come up with a transformation that makes sense for it, so that they're all in the same coordinate system. That may mean, depending on what we're doing, scaling the building down so it makes sense in the context of the bird, or scaling the bird up so that we can actually see it relative to the building, or even doing just relative placement of the bird in the building so that while they're individually defined in their own object coordinate system in which they're each at the origin of that coordinate system, they're not going to want to be on top of each other. So we're going to displace some, scale some, translate, rotate, do all the transformations we were talking about. That's so-called modeling transformation. And then separately, we also have to consider where is the camera? And again, if you don't like think of it in terms of camera, where is the viewer? Where is the human eye looking at the scene? Am I at ground level? Am I floating in the clouds? Am I inside the building? Where is the actual viewer of this scene? And that's the so-called viewing transformation. You can think of that as moving the building to be closer to where the viewer is, or you can think of it as moving the viewer to be closer to where the building is. The transformations are equivalent; they're the same exact transformation, such that we tend to at least logically combine the two transformations into one so-called model view transformation with just a single matrix that represents both steps. I have a series of objects in their own coordinate systems. I'm applying a matrix. Literally, I take all the vertices of those objects and I do a matrix vector multiplication of each of those vertices as they come. And the end result is something that's relative to the camera of my scene. Here's where this object is in terms of XYZ location relative to my camera. And you can call that camera coordinates or otherwise known as eye coordinates. That's the initial part of this viewing transformation pipeline that we have here. So we have world coordinates is that sort of common coordinate system. The eye coordinates are the world coordinates from the camera's perspective. So another way to think about this is a somewhat abstract version of it. But we have a coffee mug or something here, which is in its own object coordinate system, very likely centered at the origin because we're defining that object in isolation. We want to bring that coffee mug, coffee cup, from its origin to somewhere in a world where there is a table. That would be the world modeling transformation, put it in world coordinates. And then we have to figure out for this coffee cup on a table, you can't see that too well, for that coffee cup that is on that table, where are we looking at it from? Where is the camera? And that's what this is supposed to indicate here. That's a very quick drawing of a human eye or just someone viewing the system here. So Matt asks a good question about what is the field of view of the camera, and that actually tends to get separated out. So we have this first set of transformation, which is the modeling and viewing or model view matrix and model view transformation, where we're kind of situating everything, including the location of the camera. Where is the camera and what is it looking at? And it turns out those transformations can be thought of as equivalent to each other. Moving the mug closer to the camera is the same transformation as moving the camera closer to the mug. And that's the best I can explain that concept. Where we want something closer, it's the same transformation. You can think of it as being in either case. We're either moving one thing closer to the other or the other thing closer to that viewer, but it winds up being the same math that gets applied to the incoming vertices. We're not transforming a camera in practice, right? There is no actual camera that we're seeing in the scene. It's the objects we're wanting to view, our geometry in our scene, and we're transforming where we're placing these in our XYZ space so that we have things relative to a camera. And then there has to be the actual transformation that corresponds to the camera catching something, capturing what is in the scene. And that's where we're starting to do that 3D to 2D step. All this is 3D so far, right? 3D positioning of objects, 3D positioning of the camera. And then we have to figure out what it means to do that projection, how we go from 3D down to 2D. And that is in that next step, that projection transformation, where we determine things like the field of view, aspect ratio of the camera. How much of that scene is this camera going to capture? And what are the characteristics of that camera? The analogy gets a little bit tortured because the math winds up being a little bit different, but you can think of it like, what is the type of lens that I'm selecting in my camera? It's close enough of an analogy that I think it works well enough for the level of theory that we're going to get into. Okay, previously we specified where things are relative to the camera, and then in that projection transformation, which is going to be its own separate matrix, which is going to look a little different than the model view matrices, that is the rotations and the scaling and the translations. We're going to figure out what kind of camera it is. And ultimately, and we will talk about this, the idea of that projection transformation is we kind of normalize everything. Everything that we're going to want to be able to be visible by this camera is going to fit into a cube. A 2 by 2 by 2 cube centered at the origin. That is a little reductive. That is the definition of that projection transformation we're doing here. We're defining the viewable space of that camera. Right, the camera doesn't see everything, right? The camera has a certain focal length. The camera has a certain aspect ratio, has a certain field of view associated with it. So it sees certain things in the scene. It's not guaranteed to see everything. That is encoded as a transformation that places all the objects that should be visible in a 2 by 2 by 2 cube. And we'll work a little bit our way through the math of how we would build up those projection transformations. There is potentially to deal with perspective, which we will also talk about a separate division step that happens at that point. But then ultimately, what we get is our objects in this normalized device coordinates. This range -1 to 1 in our x, y, z dimension. There's a step that's not shown here where if something is not actually going to be viewable, so this coffee mug should probably be viewable by the camera, but if there was another one significantly further away, perhaps that would fall outside the range, there's that separate step. That's where our actual clipping would come into play. We talked about clipping in the abstract. It is part of this step. It happens after we have a guarantee that things we want to view are in that range of -1 to 1, and we would clip things that are outside that range, -1 to 1. And then finally, we have our scene where things are projected down to 2D. One way we can just do it is by just encoding the depth information separately. Other times we just drop the Z information entirely at that point. And then we would figure out what that means in terms of our window. That's our viewport transformation. And final, render output step where we determine whether the actual fragment should go to our color buffer or not. So the reason we've been able to get things to work so far this semester in terms of doing things in the lab is up until MP3. We've basically started right here, right? We have required, I've been calling it our idiomatic OpenGL, but our very restrictive subset of OpenGL that actually will work for us. We've been requiring that things are within this range by default, -1 to 1. If you were to provide input geometry for your test applications before MP3, that was in the range, -100 to 100, you get all sorts of weird results because we're not doing up until this point any of these other steps to try to get things into those normalized device coordinates. And even in MP3, in which we can do a lot of these transformations, as many as you can get to work in terms of the math in your shader core that you're building, we're actually still not doing clipping yet. And it's not clear we're actually going to get to clipping at all this semester. It's a valid project idea for your team to implement that. So while you don't have to specify all your geometry in the range -1 to 1, you can specify it in your object coordinates, going back to our building analogy here, or whatever coordinate system makes sense to you. But if you don't want your things to be wrapping around the screen and just otherwise looking kind of unpredictable and weird, you still have to maintain that after you apply your modeling, viewing, and projection transformations in MP3 here, that things actually still fit in that -1 to 1 range after the fact, because we don't have any hardware that gets rid of our geometry that doesn't actually fit in that range. So this is the big picture of what I wanted to talk about today. So previously, on Tuesday and before, talking about the basic math. What does it mean to do a scaling and a rotation, and the shearing and some of the other transformations? So that's just the basic linear algebra, how it applies to arbitrary objects. Now this is just an application of that same math. So there's really no new math today. It's how do we build up these matrices to do what we want them to do? What are the OpenGL hooks to allow us to do that? And what does the end result tend to look like from the perspective of the output scene here? And I think I got that. So we're clipping, and then finally we have our viewport coordinates where we then translate that ultimately to the screen. So let's talk a little bit again about the actual projection and the actual setup of the camera. This analogy only goes so far, but it is the intention of the OpenGL camera model of rendering a scene, which is equivalent to wanting to take a photograph. And right, what ultimately happens when you want to take a photograph, right? You have some 3D thing in life, me at the beach, right? You want to take a picture of something that ultimately is three-dimensional because that is our reality, right? And the ultimate thing that you get back out is this two-dimensional result, ignoring stereoscopic cameras and VR and all sorts of things, traditional photography, right? So what would you do, right? Well, depending on the type of picture, in theory, you would position your camera, right? So set up your tripod if you're an old timer like me, and point the camera at the scene. That is your viewing transformation. Where is the camera in my scene? You would then potentially, depending on what you want to do, tell this person to move over this way, tell this person to move in front. You'd position the objects in your scene. That's your modeling transformation. That is what you want to be in the scene, the objects relative to each other. Then, in theory, you have a million options on your camera, including things like adjusting the zoom of the camera or changing the lens of the camera. That is what's going to be encoded in the projection transformation. And then finally, you've taken the picture. Some things were captured, other things did not make it into the picture you take, and then you want to kind of print that picture. You want to scale it up or down. You want to print a poster. You want to print a little 3x5. That's the closest analogy then to our viewport transformation. Or ultimately, where do you want to put that picture on a screen relative to other pictures? That's your viewport transformation. So those are the steps that one would essentially do. Maybe we do that in such an automatic way we don't really think of it that way. We hit autofocus and hit go and don't really think about it. The camera's doing a lot of that work for us. But that is the analogy we try to follow when modeling a three-dimensional scene and applying these transformations in our OpenGL. And another way of looking at it, although it's very similar to the previous slide, is something like this, that we have different ways of encoding effectively the same exact thing. And the reason I say that is, as I mentioned before, is because we want to figure out where we're looking at the scene, where our camera is, and we want to place the objects in our scene relative to each other and relative to the camera. But ultimately, while we may use slightly different verbiage to describe what we are doing, it's the same exact math. When we think of objects, we do tend to think of our objects. This is our teapot, like the example from Tuesday of translation, moving it around, rotating it, scaling it, making it larger or smaller. Whereas when we think of a camera, we don't think of rotating our camera or translating our camera. We think of maybe placement of our camera, physical placement of our camera, and pointing our camera. So that's two different things we're specifying. An XYZ location for the camera, and then a direction the camera is actually pointing. And it turns out we also have to declare which way is up, because even given an XYZ location and a direction we're pointing, that doesn't actually tell us all the different permutations of how we've rotated the camera around that origin. But essentially, where is the camera located? Where is it pointing? But those are the same two things. Moving my teapot closer to the camera could be thought of as a translation. Moving my camera closer to the teapot can be thought of as a positioning of the camera, but they both correspond to the same math. Taking the vertices that we use to specify for all the locations in that teapot, all the different triangles associated with it, and changing them via a translation operation so that it's closer to this location I've defined as the camera position. So another good, thanks, Matt. I do appreciate it. So I guess what I'm trying to get across, and I'll try it one more time, is that we can think of those two operations as being separate. One is modeling. I have a teapot. Where does it go in the world? You're calling them global coordinates. So the other term that's commonly used in the OpenGL world is world coordinates. Where do they go in the world? And then we can think of where we place the camera as a separate thing. Put the teapot here, or the coffee mug, or whatever it was, and put the camera over here. The big picture takeaway is that while sometimes, given the type of math we want to separately apply in a shader, we like to separate out the modeling from the viewing. And that is sometimes the case. Logically, it's the same exact math. And we don't really do one or the other. We just do it. And we specify typically, in old school OpenGL, we specify it specifically with a mode that says, please set my model view matrix as a single matrix. In shaders, you've started to see those uniform types in our shaders. And a very common thing in a vertex shader we would specify would be a 4x4 uniform called the model view matrix. Sometimes it's just called M, other times it's called MVP, but model view, MV, depending on what you want to do. Sometimes you want to split it up, other times you just encode a single matrix. And we just specify it once. And then for every vertex that comes in, it doesn't really matter anymore whether we were concerned about the teapot being closer to the camera or the camera being closer to the teapot. It corresponds to the same exact matrix. And we just apply that matrix vector math as we go. And I like a couple of these sort of old school OpenGL. Yeah, potentially. So thanks, Brian. So yeah, it depends because depends on what we want to do with each of the individual objects. So we may have to compose them separately if every object needs a different scaling factor and a relative placement from each other. The way it oftentimes work is you could specify for each individual object an individual placing, and then as a separate transformation, figure out where they are relative to the camera. Yeah, and you're right, though, that for a lot of these demos, I possibly for that reason, because the code starts it's already a little ugly, and it starts to get pretty ugly when that's the case. Um, there is a lot of matrix bookkeeping code in your OpenGL. And I know that you haven't seen any of it yet in the code that we've been doing all semester. Starting now, that's going to change, right? Because uh, that's the fundamental thing we're doing when we're setting up any three-dimensional scene, which is where is the camera, where are the objects relative to the scene. That's not even talking about projection yet. Ultimately, we can also combine, in many instances, the model view matrix with the projection matrix and get a single, you'll see it referred to as the MVP model view projection matrix. Other times, for different shading purposes, we may want to keep them separate. Um, but so much of your OpenGL code tends to be that defining the camera for the scene and determining what the viewing should be for the scene. So this is kind of an old school OpenGL code to show the equivalency between a couple different operations, specifically the modeling and the viewing operation here. We don't use the old school OpenGL 2.0 type of stuff anymore, but as you've started to see for a couple other examples, all of those functions are still extremely useful. And so it's very common in OpenGL if you're writing just raw OpenGL versus using a game dev library or something in which they would provide their own versions of these type of functions. But it's pretty common in just straight OpenGL code today that even if you don't use any of these so-called fixed function things that does a rotation or does a scaling of a matrix in the OpenGL state itself, the GLM library has an equivalent function for doing every single one of those things. So for that reason, even these demos that are using OpenGL2 code is still pretty useful. And you can do a one-to-one replacement with GLM calls. The only difference then is you have a GLM function for things like translate, rotate, and scale. The end result of that call doesn't actually change your OpenGL model view matrix. You then separately have to update the uniforms, the actual matrix in your shader, and hopefully you're starting to look at a little bit of the plumbing of that for MP3. Uh, you use all those GLM functions to update a matrix in your application memory space, and then via a single OpenGL call, you then pass that uniform, update the uniform with this new matrix that's been calculated. Because this way of thinking about a three-dimensional scene is still extremely relevant and powerful. These functions themselves are just a very inefficient way to specify the transformations we want to do because they correspond to fixed function hardware in which we'd be updating basically a single physical matrix stored on our chip. And we don't do that anymore. Now we have shaders that have an arbitrary number of matrices or a large number of input matrices. We can still use then the equivalent functions in our sort of helper library here, and then just update the matrix pointer effectively in our shader code for the next call, for the next pass of vertices through our vertex shader. But the point of this application, let me open it up here, is not to necessarily go through the GLM code, which I think is relatively straightforward to understand. At least it's pretty well documented. We all complain about things that aren't documented well. I look at that GLM library, and I'm personally pretty content with. If I want to do something, at least the API is documented. You can try it out and figure out a way to get it working within a couple of minutes. This application, which is using the fixed function calls, for which there is a GLM call equivalent for each of these, is meant to just visualize and try to illustrate the equivalence between the modeling and the viewing transformation. So here we have a picture of my car, menu car, and what this is attempting to show is both what you would get as sort of the output of your render. So this is the screen space view. This is a viewport showing what actually should be rendered based on the camera positioning and the set of transformations applied here. And then this is just for demo purposes, for educational purposes, also showing that there is no physical camera in the scene, right? There are no actual physical arrows in the scene. Separately, as part of the application, set up a view of the scene in which there is an actual camera and attempt to visualize what's happening with the camera here. Why this camera capture is of this particular shape, we'll talk about in just a moment. But this isn't meant to illustrate the different changes there. This is just meant to illustrate the model view transformation. So we have our geometry for our object here. And we may want to move it somewhere else in the scene. We may want to translate it left or right. And we can do so via those updating a uniform matrix in our shader or calling the equivalent of a GL translate function to translate it. But I want you to look at both what's happening, assuming everyone can see that relatively well here. It's a little dark on my screen, but assuming you can see it, we can do that by specifying here. And I want you to look at what's happening in both upper left and upper right windows here. I'm specifying GL translate to now be some different value. Okay. Zero point 0.7, it was a sliding scale, some arbitrary value. I changed the X parameter of the GL translate, updated what that equivalent matrix would be. Go back to Tuesday's lecture if you want to see exactly what that matrix looks like. It's relatively straightforward. We're adding 0.79 to our x component of all of our input vertices. And by adding 0.79 to the x component of all our input vertices, we've moved them all 0.79 to the right in our object space, whatever that corresponds to for our scene. In this particular application setup, that is set up so that's a meaningful amount and that you can still see at least most of it here. So you can think of that modeling transformation as having moved that car to the right, and that matrix is having encoded a moving of that object to the right. But it is equivalent. The math is equivalent to instead specifying that I'm moving my camera to the left. And I can show it again. You might have just been looking at the car when I was doing it the first time. That's close enough. There might be a reset. There you go. The actual car is moving to the left. Or excuse me, the car is moving to the right. The actual camera relative to the car is moving to the left. Same for when we want to then look in the Z dimension here. We haven't been doing a lot of depth processing because our hardware doesn't support it, and it still doesn't support it, but it's still relevant for our 3D setup here, right? We would then be increasing our Z parameter of the value. Maybe let's move this back to the center first. We're going to increase our Z parameter here. And what happens? Is our object moving closer or is our camera moving closer? It's both, right? It's exact same transformation that's happening. And what do we see happening here once we've moved our Z far enough forward? Well, our camera has moved so far forward that what our camera is now taking a picture of is actually inside the car. Maybe we want to do that. Well, for this geometry, probably not, because no one put any effort into actually specifying any interesting geometry for the inside of the car. But this also illustrates that kind of clipping phenomenon as well, right? We need, as part of that transformation, we were talking about line clipping and a little bit of polygon clipping, possibly Ryan, that we need to specify things that are outside our range of valid things to be viewed in the scene. And it's not a binary thing for the object as a whole, right? This object as a whole, this car is a amalgamation of just the individual triangles that are used to specify. Maybe it's triangle fans and strips and things like that. I know we still have some triangle strip nightmares from last week. So we're doing it on a triangle by triangle basis, and we're determining what portion, if any, of those triangles are actually to be showing up on our scene. You can think of it as the car moving closer to us or the camera moving closer to the car. And the same for all the remainder of the rest of these transformations. I have scaling in the X factor here. Ultimately, at least now in modern OpenGL hardware, there is no vertex scaling hardware. All of these specifications are updating that model view matrix. So am I making my X parameter wider as I increase the X scale and stretching that car? Or I'm actually just changing the viewing matrix such that we're viewing with a tighter field of view associated with that camera. It's both. It's either. It doesn't matter. It's an equivalent transformation. And same for all these. And so maybe in the Y, you can really see it in that extreme there. I don't think there's any replacement for playing around with this yourself. Not this application, but playing around with those transformations yourself. You can look for OpenGL help online. It's such a common refrain. I can't see my image. Where did my cube go? I lost my cube in the scene. It always has to do with where is the placement of your camera in your scene? Where is the placement of your object in the scene? And is the object in your scene that you're interested in viewing actually within the viewing structure that is specified by your camera? Because certainly, if we translate this, and it wouldn't take much, right, to translate this far enough so that we don't see anything at all. But it's there, right? And there were some good questions on Discord about, Why do we need to do clipping? Can't we just wait till final render output or relatively late in the pipeline? Well, for a single car, that's probably okay, right? But a common way to set up a three-dimensional scene is to specify nearly all of the geometry for the three-dimensional scene and then rely on hardware to very aggressively get rid of the geometry that actually isn't relevant for your final projection for that particular frame. Because the camera itself, I'm dragging and dropping it very quickly here. The camera itself could be updating as fast as anything else in the scene, 60 frames per second, 120 frames per second, whatever it may need to be. And so consequently, we need our hardware to be very aggressive in doing this math as effectively as possible and getting rid of what it doesn't need to see as effectively as possible. So that example I think is helpful for kind of seeing the equivalence between modeling and viewing. It's not misleading, but it's actually showing too much in a sense because it's also showing a projection that's happening. And I just talked about projection in very hand wavy terms. When you hear the term um, projection, it means a lot of things, but in the linear algebra sense of the word, it's reducing dimensionality of your data. In this case, it's almost always referring to in the graphics context, going from three-dimensional down to two-dimensional viewing, which makes sense. We have three-dimensional scenes, and ultimately, generally, a two-dimensional screen we want to project something on. Matt brings up a point about uh, a lot of modern graphics hardware is dedicated to being as aggressive as possible as doing early optimization. So, level of detail optimization is one such thing. There's a lot of things that can be done to try to as aggressively as possible, given all the number of vertices in the scene, to cut down on that number as early and as soon as possible, as opposed to waiting till as late as possible. But going back to projection here, it turns out that at least in OpenGL, we specify two fundamentally different types of projection transformations. And I'll get into a little bit of the classical viewing taxonomy. I don't personally think it's terribly interesting. So if I don't think it's interesting, you may or may not find it terribly interesting. But at the very least, I think it's important to compare and contrast the so-called parallel projections. You'll hear me use the term this orthographic projection, which is not as realistic for what a modern camera would provide you, in which everything is projected into a flat plane. Effectively, although we can do a few other things along the way, effectively take everything that we've specified in three-dimensional space and just drop the z component entirely. We are doing that so far this semester. So when you open up a couple of our three-dimensional applications in MP3, when you have MP3 working, they're going to look a little flat. Things are going to be drawn entirely on top of each other. If you really would want them to look good, we'd have to go back to those object space approaches, of like the painter's sort. Draw the background objects first, then continue to layer on so that things still look pretty good. We don't have our depth space approaches working at all yet, but that's an orthographic parallel projection. We take our three-dimensional scene and all rays of light hit the projection plane equally, and we get everything just parallel as to where it is. Whatever is closest to us is what we see. We see nothing else behind it, and then that's contrasted to a sort of perspective view of our scene. And in the perspective view, there's an origin. So it's not just a camera that's at a location. There's the center of focus or center of projection associated with that camera. And we're doing a few things in terms of our matrix composition for the perspective transformation. But ultimately, there's some division by z. Another way to think of that division by z operation, things that are further away from the camera should appear smaller. That maybe makes some logical sense, right? You see that tree that's a quarter mile away, it should look smaller, even if it's the same size tree as the tree that's right next to you here. And that's what the perspective transformation is attempting to do. That's one way to think about the math that's ultimately happening here. We can create our matrices such that we will do a division operation after the fact that will make the things that are further away appear to be smaller. Very briefly, I'll talk about classical viewing here. I want to make sure we get through all of this today so we can move on. We'll do our best. Um, we talk about classical viewing. Now we're back to the camera with a tripod again. But you have three things that's required. You have one or more objects you actually want to view. You have the actual viewer, the camera, with a surface associated with that viewing, and then some way of modeling or capturing projectors, the rays of light that cast from the objects themselves to the projection surface itself. So classical viewing is all about what is the relationship between these objects, and we tend to, if we take this uh, classical viewing of buildings in that field of the planar geometric projections that happen in that field, we tend to care a lot about the principal faces of the objects that we're interested in. This is still very relevant when we're doing 3D CAD viewing, either of buildings or of just three-dimensional objects in our computer-aided design. It's a lot less relevant for looking at realistic-looking scenes, um, but at least it allows us to understand what's happening as a difference between the parallel projections and the perspective projections. So the parallel projections, and again for CAD work or for architectural work, you have your um, particular object you're interested in viewing here, and your projectors are parallel to the projection plane. Everything just goes straight through and doesn't converge at any point. Or another way to think about that in practice is that you do have a center of projection, but mathematically it's actually at an infinity. So there is ultimately a center of projection, but it's infinitely far away. So from the perspective of the view that's happening here, everything is parallel to the projection plane. So for our more realistic looking computer graphics, where we're trying to make things look like the things that they are, and we're not trying to provide an architectural or CAD view of a system, you would have some center of projection, and the projectors themselves would converge at that center of projection. So you do have a whole taxonomy for the different types of classical projections, and it almost always has to do with architecture and buildings. And you want to look at the front elevation versus the elevation oblique, or an isometric view, a 1 point perspective, there's a 2 point and a 3 point perspective. I don't know how much that matters. If you catch me throwing out some of those terms and not defining them, please call me out on that later. I think for our perspective, and we actually tend to use orthographic and parallel as synonymous terms, although technically there's a subcategorization here. We care about the difference between the different types of parallel projections and the different types of perspective projections that we're doing here. The math works out to be the same. At least the hardware itself has evolved to treat both cases as just identical processing on different looking matrices. What that means for what the matrices look like is what we'll talk about today. But the actual computation, what you have to do for MP3, by and large, your hardware is agnostic to the type of projection that's happening. It is going to get as input a matrix. In this case, it's going to get as input the projection matrix, separate from the model view matrix, maybe combined with the model view matrix. And from its perspective, from its point of view, it doesn't matter. Input vertices come in, model view, later projection matrix gets applied to it, output vertices go out. I think you can take a look at this offline as well. So parallel projections is where you can look at one side and really focus on one side. Even if you have an isometric view, you're getting angles that, if they're in faces parallel to the projection plane, they're preserved, but you can still kind of see around the object as well. So from an architectural view or a CAD view of an object, it can be fairly useful. It's actually not something that necessarily corresponds to a traditional camera. Um, with telescoping lenses, you can get something equivalent to a parallel projection as you're taking a photo. Um, those tend to be very misleading, right? They can make one object that is 1,000 foot away from another object, look like they're right next to each other. So they are bearing all of that depth information. You can get something close to that in architecture. There's this concept, of a bellows camera. You can get something very similar to that, but it doesn't tend to correspond to something that we would want to view when drawing in the physical world, right? Because in the physical world, things actually do have perspective. Things that are parallel in the physical world, as we view them, this edge of this part of the building and this same edge, opposite edge of the same building. Um, from an architect, it's important perhaps to see those as being parallel to each other. As we see them in practice, as we're actually looking at those buildings, things that are parallel do not necessarily look parallel. They converge at some point, right? Some center of projection, right? So we tend to see things in real life with projection. So if we care about realistic looking scenes that we're trying to render, we care about processing our input vertices with a projection transformation that includes that perspective information, right? Parallel things do not look parallel. Things further away should look smaller. This is, he's now 12 years old. This is my son. He is not nearly as tall as the Washington Monument. So, believe it or not, that picture is slightly misleading. Another way to think about that is, in art, things just tend to look more realistic when there's actual perspective applied. This is this is a misleading example, but still, before perspective, everything was just drawn on top of each other, and it had this kind of two-dimensional feel to it, where you see everything with very little perspective, and everything's drawn on top of each other. Versus, after artists started to understand what it would mean to apply perspective in paintings, there was no before perspective and after perspective period in modern art, but just an example of an artist who didn't take that into account, perhaps intentionally, and one who did in fact take perspective into account. So we have this concept of vanishing points with our perspective views, where we're going to have parallel lines in our object not be parallel when actually projected to our projection plane here. They're going to converge at a single point in some distant depth from our vanishing point. If we want to draw perspectives by hand, we have to actually take that into account. And so this type of drawing, in which this line and this line are parallel in practice but are not parallel when actually drawn together, is a little bit harder to do. But architects and others who want to do realistic drawings of views with perspective have to take that into account. But to make it look realistic, we have to have that foreshortening. We have to be able to take distances that are equal along the line that are no longer be projected to equal distances. Objects that are going to be further away from our camera have to appear smaller than those that are closer to our camera, and only certain types of angles are actually going to be preserved. So it can be done by hand. It's a little bit more difficult to do it by hand than otherwise. Um, but by computer, as we find out here, it's just a different matrix that we have to compose. So by composing that different matrix, the math in hardware winds up being identical for us. I had an exercise planned here. I think we're going to skip it for now. So, how to support the various traditional matrix loading and transformation operations. I'm gonna skip it now. Little bit closer to your MP0. Basically, it'd be designing a hardware for MP0 in which we can dynamically change the matrix. And in 480, several years ago, that was our lab experiments for like the equivalent of an MP3 for the earlier versions of 480, building fixed function hardware. It's fixed function, right? We have hardware that does the matrix vector multiplication with hard coded logic for us, but we still need to be able to support dynamically changing the matrix. And so there's the functionality that allows us to do it. I don't think, I mean, we have a bigger challenge ahead of us in MP3, so I think I'm going to skip that for now. It made sense to do this at the time I put this together. In the interest of time, I'd like us to move on. So going back to what our steps of the viewing process, right? We have our camera. We have to position our camera. That's our model view matrix. We have to then configure the camera. What is the focal length? What is the type of lens we're using for our particular camera? That is going to correspond to a projection matrix. And then finally, what is the range of objects we want to actually wind up being viewable at the end of all these transformations? That is part of setting up the projection matrix, but that's also can be thought of as setting a view volume. The reason I separate these two is for the same reason I was separating the modeling and the viewing matrix. These two operations are actually going to be equivalent to each other. We can set up a view volume, and it's going to be a three-dimensional shape we can set up. Or we can configure a camera. They wind up doing the same exact thing. The difference is what type of API call or what type of reasoning about your scene makes more sense to you. Does it make more sense to say everything within this volume is what I want to be able to see? Or does it make more sense to say, here is how I'm going to configure my camera? Just like modeling and viewing, as that one little application showed, are equivalent to each other, configuring a camera and configuring a viewing volume via a projection transformation are equivalent to each other. Ultimately, it's a separate matrix now we're configuring, and it's going to correspond to what we want our scene ultimately to look like after we've already specified where the camera is going to actually be located in three-dimensional space. Now we're going to separately specify what kind of camera it is. So this step, that was that previous example with the car. Now we're going to set up what is that viewing volume, or if it makes more sense to you, think of it this way: what is the type of camera that we're specifying? So this gets us to our OpenGL camera. So we have been doing a lot of work so far, as I've mentioned, with kind of OpenGL defaults, right? So initially in OpenGL, if you don't specify any of these things, there is no transformation happening. So our object and our camera frames are exactly the same. So your default model view matrix, if you want to think of it that way, is an identity matrix. In fact, one exercise you should do for MP3 as a way of testing that your vertex shader works, right? So right now, the vertex shader we provided for you allows you to physically pass through these vertices, right? Um, it doesn't engage the shader core at all, so it doesn't really test anything other than you've gotten Vivado to work again this week, which is itself an accomplishment. But that's all that it's really testing, that you were able to export cores and reconfigure a bit file and all that. The next step, which could make a lot of sense as you're starting to get more and more of your functionality working, would be to just test it with identity matrices, right? If we take an identity matrix, right, ones on the diagonal and zeros everywhere else, that should effectively not transform our input vertices. That would allow you to test all of the previous examples that have worked for your team, all the MP1 and MP2 examples, actually executing shaders for each of those vertices as they come through, but the end result should look identical. And that's a good sanity check, because in theory, although it's possible, depending on how you implement it, there's still some bugs you have to find. In theory, if it works for an identity matrix, it should work for any arbitrary matrix. At least in theory. I think if you get to that point, you're extremely close to being done with the assignment. And it's a very good sanity check to know, I know what the output should look like. I'm quote unquote transforming the vertices, but I'm not actually changing the values from input to output. I'm not just strictly passing them through. I'm loading them, I'm taking them off the FIFO, I'm executing instructions, and I'm doing this matrix vector multiplication via my SIMD processor core. But the output's going to be the same as the input. So it's pretty easy to check, both in simulation as well as on the board, that hardware is working with an identity matrix. And by default, if you don't specify anything else, that's what these uniform values are going to be for you. Certainly in your fixed function hardware, it was going to be an identity matrix. And in our shader core, if we don't specify something, you'll get an identity matrix back out. Well, we have to think about that now, what that really means. To have a model view matrix be the identity means that we're just not applying any transformations to our object. So our object coordinates are our world coordinates, are our I coordinates. Likewise, by default for the projection transformation, there's a camera that's located in the origin and just has a 2 by 2 by 2 cube centered at the origin. That has worked just fine for us. We've not even been providing z values for our input vertices. So the fact that everything is at z equals 0 works perfectly well for us because our camera is also at z equals 0. But it's a quick thing you can check with your MP2 or even MP1 examples. Change any of the z values to 0.1 for any of the applications, or 0.001, it doesn't even matter. Change it to anything non-zero greater than 0, given where our camera is pointed by default, and everything will turn black again. You won't see any of your vertices, any of your geometry on your screen. So you could argue that all of our previous applications are working, coincidentally. I mean, it's intentional, obviously, the way we have it set up, but it's taking into account sort of the OpenGL defaults, which is model view is an identity, projection is a parallel projection centered at the origin pointing in the negative z direction. Consequently, if you specify things at x, y, 0, they'll show up on your screen. So that's a way of visualizing what's happening with our default projection. So by default, it's that parallel projection centered at the origin with the viewing volume being this 2 by 2 by 2 box. So anything that falls within that range of -1 to 1 in our x and y dimension and is between 0 and -1 in the x dimension should be projected onto our plane. If we now want to move the camera front frame, we now know how to do that, right? We can specify these translate, these rotate, these scales, but we can also specifically use functions that allow us to directly position our camera. And I won't show the example of that because it's very similar to the previous example, but specifically, There's the old school look at function, but the GLM also provides a lookup function, a look at function. And in the look at function, we're specifying three things. I think at first glance, two of them make sense, and the second's a little arbitrary sounding. But you first specify an not really an I vector, but an I vertex, a three-dimensional point for where the camera is located. So call it camera or call it I. Where's my camera physically positioned? The center of projection for that camera. What am I looking at? That's my at vector. And then finally, the third one, which you may not realize, and you can use some defaults for that as well. Which way is up? Because technically, you can position the camera, position where it's looking, and then there's still an infinite number of ways it can be rotated around. So you want to specify which way is up corresponding to your camera. So an example of what that cube aligned with the axes would look like would be specifying, this would not be the default view, but this would be look at where we're specifying the value at location 111, looking at the origin with up being 1 in the y dimension here. Question in the chat I wanted to get to, will our rasterizer need to take z into account? Well, my snide answer is your rasterizer does take z into account and you don't realize it, right? In theory, at least. But this will be painful if we have to go back to MP2 code, but it may happen. In theory, your rasterizer was interpolating all the attributes, including z, because it does matter, right? Because z is fixed per vertex, but then would be varying per triangle, right? So you would have this three-dimensional shape, and depending on how we eventually hopefully do this clipping, but even independent of clipping, depending on our depth buffer implementation, we may wind up with triangles that are intersecting each other. And with a depth buffer, the only way that works is if each of the fragments themselves have a valid, appropriate z value associated with them. So even independent of clipping, which we may not be actually implementing this semester, even just for getting proper depth buffering, you do need to rasterize the z values. My belief is you probably did, even if you didn't realize you did, because if you rasterized all the attributes, you would have gotten z for free. It was one of the attributes you would have rasterized. You probably didn't test it because we haven't been testing anything with z. We're still not really testing anything with z. So you'll catch that pretty early on in MP4 just with the data that you're seeing, whether z is actually varying, if it is varying from vertex to vertex in a given triangle. And if you see that, I think at that point the fix won't be too painful, but it'll be a little painful. You'll feel like you're going backwards, but I'm guessing most groups did that, but we'll see. So for your default projection, your default parallel or orthographic projection, so for points that are within that default view volume, you just drop z. That's our way of doing projection. We just entirely drop z. So we take our actual post-projection x value to be whatever's at that point, y is whatever's at that point, and z is set to be 0 if it's within that default view volume. Most graphic systems, and certainly OpenGL, use this concept of view normalization. So that is the default projection, that 2 by 2 by 2 cube. And all of these other non-default projection transformations that we may be interested in for perspective and for just changing the way the camera is viewing and where it's located, effectively are one way of transforming all those other views via that matrix to that same 2 by 2 by 2 cube. So let's look at what some of those matrices might wind up being. So if we just want to take our values and drop z, this would be a matrix that would apply to us. Oftentimes you see in systems that we still want that z information later on, but at least in theory, what you can do is just take that matrix, identity, identity, identity for x, identity for y, drop z, identity for w. That's kind of your default orthographic projection. That works if you want to have that parallel view of a scene there. If we want to have some perspective, well, then now we got to look at a little bit of the geometry of what that means to have that perspective. So in our perspective view, we now no longer have kind of a parallel projection plane. We have a center of projection in our virtual view, our camera that we have here. Instead of a cube that we're considering visualizing in our system, it's actually a frustum, right? So it's a pyramid with the top cut off. It's a parallelepiped, which I can never pronounce correctly. But it's this view in which you have a far plane, a near plane, and given an aspect ratio, you have this width over height ratio corresponding to this plane. So you're specifying several things for a perspective projection. For a parallel projection, you're specifying a cube, so near and far, left and right. For the perspective projection, you're also doing front and back, and then you're also specifying what the aspect ratio would be. So for a very simple perspective transformation here, um, you would have just the center of projection at the origin with a projection plane at some location d at some value for z equals d. If it's pointing the negative z direction, d would be less than 0. And then if you look at what the side views of that projection would correspond to, given a point xz in that space, you would wind up with a new value, excuse me, given a point xyz in that space. Looking at the view from the side, it's just hard to visualize this in 3 dimensions. So looking at the xz dimension separately from the yz 2 dimensions here, you would get a point that is linearly scaled by that viewing plane here. So you'd get a new point x, or it'd be x divided by z over d, same with y, and with z would be whatever that depth plane would be. And we can provide a homogeneous coordinate form of that matrix in which we're really not scaling x, but instead we're going to scale that w parameter that we have here. This gives us, for xyz1 as an input, we get xyz and then z over d, which at first glance doesn't seem right. That's a good question, Nathan. I'll try to explain what's happening there. Let me reflect on that a minute, because this part's a little bit subtle. I don't know if it's at this point. It's hard for me to know whether it's interesting to you guys or not. What's happening here? So there's two things I'm trying to explain. So this is generally our perspective view, and we do have to specify a far clipping plane here because they're ultimately to calculate a perspective, we have to know what the aspect ratio would be. And so that's a relationship, just as we specify, between the near clipping plane and the far clipping plane. You can push that far clipping plane as far back as you'd like, potentially. Likewise, you can move this near clipping plane as close to the camera as you'd like as well. And so by default, that's what we were doing here with it centered at the origin. So for that default one in which it's centered at the origin, we're really just scaling our x and y by that z over d value. The rest is all just mathematical tricks, basically. This is the projection transformation. We are done. What this next is I'm attempting to explain as best I can right now, is what does that correspond to? Not quite, Brian. What that would correspond to, because we are taking those values and we're projecting them towards the center. It's just kind of hard to see in 3D. I don't know if this shows it really any better. So we have an object that's far along on that plane, and it gets shortened depending on how far away it is from that projection plane there, from where our camera is located. So given a center of projection at the origin, we have an actual XYZ value, and because it's no longer a parallel projection, those XY values are also going to be scaled. I think for now you can take my word for it that is the scaling that's happened. I think that x becomes x over z divided by d, y becomes y over z divided by d, and z is just at the projection plane there. That's the math of the projection transformation. Where it becomes relevant to our MP3 and other OpenGL related goals here is, by default we cannot specify that that's not a linear transformation anymore, right? There's no matrix that gives us x equals x divided by z over d. There's no way to specify via a series of linear transformations that operation that is nonlinear. The trick, or the approach that is used in all modern 3D graphics hardware and the modeling associated with it, is we actually get that scaling factor by not scaling x, y, or z at all in the projection transformation matrix itself, but by instead scaling that w component there. So if you take this matrix for xyz1, you get xyz z over d back out. That, I think, you can trust me on, or you can see that as you apply that here. And then there is a separate step. So after we do this perspective-based transformation, I have to be a little bit careful here about, we must divide by W. Our convention is then we have a perspective division. We have scaled the W component, and as I introduced the W component, it is a homogeneous coordinate that gives us the ability to apply both translation, rotation, and scaling all using the same matrix here. And the assumption is all of our geometry is specified with W equals 1. Both from input side, generally, almost always we specify W equals 1 when we're specifying our geometry, and then all the way through the pipeline. So to get this perspective transformation to work properly, we're actually doing an extra separate step here. We're specifying for this very simple case of a perspective at the origin that matrix that is only scaling the W factor by Z over D. And then separately, and it would have to be a separate piece of hardware, and getting an answer as to whether that is still fixed function hardware or whether that's just done in the shader. We can do it either way with our implementation. Separately, we have a divider that takes all the values and scale it so we're back on the right homogeneous plane, which is W equals 1. So we get an output of the matrix vector math that is W not equals 1, and then we go through and we divide all of these output values one by that Z over D value to get back to W equals 1, which then gives us our XP equals X over Z divided by D, YP equals Y over Z divided by D, and Z equals D. Let's talk about this briefly, and I may come back to this later because I think this is an important thing. I'm just actually worried about time and what I'd like for us to cover. Um, and I'll get to that question first, man. So that's a good one. So applying this many transformations would be very slow. Well, we're focusing on correctness, hopefully it'll be very correct. Yes, it's going to be extremely slow, right? You can look at what the emitted shader assembly is for just a simple model view projection transformation we want to do. Specifying a matrix, possibly doing a matrix multiplication first, or we do that in software and just pass a single matrix back out. Take input vertex, do matrix vector multiplication, store output vertex. That's going to be extremely slow on our shader implementation. And in general, these shaders, in terms of the instructions they have to run, can be quite long in terms of the number of lines of code or number of steps that are required to get from input vertex to output vertex for vertex shading. In practice, we ignore that or we amortize that cost by knowing that we just have lots and lots and lots of incoming vertices and a decent amount of shader cores available for us to do as many of those processing in parallel as we can, because the operations are generally independent of each other. To process this vertex, I don't need to know anything else about the previous vertex or the next vertex. So it's an embarrassingly parallel problem. Each of the individual vertices may have a lot of latency associated with doing that processing, but our overall throughput is still pretty decent. For our 480 implementation, it's going to be pretty slow, as you will see. It should be okay for the kind of things we are trying to do. Basic shading, basic lighting, basic texture mapping, basic transformation using model view and projection. But yes, we are building a relatively slow GPU. I think you've seen that so far this semester, so that shouldn't be a surprise coming to you today. Um, I'm just gonna bring this up right here as a thing I would like us to cover in a future lecture, and maybe it'll be something you'll come to me with wanting to know more about. So division in hardware is still not really a solved problem. Now, maybe none of this is a solved problem. There's still active academics who are working on more efficient arithmetic using modern FPGAs and other custom hardware. You think adders being a solved problem, and we're getting there, but there's still a lot of innovations being done for integer addition and multiplication. I read an article just yesterday about some innovative 64-bit multiplication that's happening. We're not alone in understanding that large multipliers are tricky. But even taking that into account, modern FPGAs have at least evolved to be pretty effective at doing integer addition, to be pretty effective at doing integer multiplication and multiply accumulate. Maybe not as effective as we would like, but to be pretty good at it. Division is still pretty much an unsolved problem in terms of, yeah, I sure will, Brian. Division is still kind of, I would call it an unsolved problem in terms of there's too many trade offs involved in the implementation to really ever trust our tools to take the division operator in your VHDL code at least and give you a divider that makes sense for your design. First off, almost all the approaches to doing division are iterative approaches, almost all of them, such that getting a combinational divider would be an extremely expensive thing, very high critical path through that combinational divider. And secondly, there's a lot of different approaches for doing division, one not being necessarily better than the other. So I think it's an interesting thing to explore. Um, in a different class, I guess, we would take the time and actually really explore the various, uh, applied math towards how we get something close to division in practice for integers. In practice, what we do as hardware designers is we tend to then fall back on, what IP core libraries are available for us. We can do it from scratch. If I told you your assignment was to build a divider, you could do it. It would take you a couple weeks. So I don't want us to do that. I don't want that to be the use of our time, our limited time this semester. So we tend to have to then generate a core, and you will see that, right? We already have a divider that was in place for MP2 because as part of the rasterizer triangle setup, we had to do a single division. And a lot of you came up with, well, if we change the algorithm some such, we'll just be adding a few divisions, but look how much simpler the rest of it is. Well, that division itself was quite expensive, both in terms of real estate and in terms of clock cycles waiting for it to be done. You'll see a divider core sitting there for you in the vertex shader and not being used. Feel free to use it. I mean, it doesn't do anything. It's just a placeholder divider core for you in MP3. Feel free to configure it, look at the different options. You're going to want to test it separately from everything else to make sure you understand that it's doing what you think you are doing. But for now, in terms of having an in class exercise where we explore some of the different estimation approaches, my takeaway for you would be it's hard. uh, you can't just do it. You can't just do a division operation outside some very specific assumptions. You can't do general integer division in hardware via hardware inference, and you have to always think very carefully. Once you've gone from a design that doesn't have a divider to a design that requires a divider, and we are here. We are here now that we want to do perspective transformations. Um, this isn't something we can avoid. By doing perspective, we now need to have a divider. We have to really think about what that divider is going to be, what are the real estate area and performance trade offs associated with that divider. And there was another point I wanted to make corresponding to that. Um, but for now, know that that does take a lot of thought in consideration for how we do division in our particular systems here. We're not going to go through this exercise then. Uh, I'm not prepared to walk us through this entire thing and to make sure we understand all the aspects of it. So, uh, sure. I do appreciate the left field question. So, Micah asks about, do NVIDIA engineers use FPGAs to test? Oh, I mean, absolutely. So, they're a little shy about sharing that information. I mean, sometimes they will share that information, but for whatever reason, the electronic design automation community, the companies that sell both the software and the physical platforms for emulation, and the actual users of that, have this weird secretive relationship. So, Intel, for example, very rarely will share whose software they're purchasing and how much of it and what kind of platforms they're building in-house versus outsourcing to Synopsys and Cadence and Mentor Graphics and others. So you will find some information. I can also share an article about that. They do. They have whole rooms of massive FPGA-based systems for doing, emulation of their designs. They get to that point when they're pretty far along, when all the architecture work has already been done, and they've already sort of understood what the trade-offs are going to be. But it's still very helpful to have hardware-based emulation because of how much faster it can still be than just building simulators for everything. So by having that hardware a little bit earlier than when the fab would be able to provide it, that's still a very worthwhile investment because you can do a lot more lower level testing, performance analysis than what a simulator would allow you to do, just based on the amount of time it takes to run the equivalent experiments in an emulated platform versus in a simulated platform. Those lines are also starting to blur a little bit as well, in which emulation is starting to be thought of as just yet another application to be accelerated. So is it an emulator or is it an accelerated simulator? Whatever it is, the goal is to be able to get it to be fast enough so that you can run more real software on it and get more real results back out. Um, but most people who have the job of computer architect um, are working with simulators all day. Most people who are in that role, because as we've maybe seen, our productivity as hardware engineers is pretty limited, right? Not your productivity, your personal productivity, just our collective productivity. How much reasonable design you can get done in any given day on an FPGA based emulator or implementation on an FPGA, significantly lesser than what you can do if you were to build a simulator for the same task or work with existing simulator infrastructure. So the answer is yes, they certainly do. Um, Comes a lot later in the process than you would expect. They eventually have to build hardware anyway, so it's not like they're wasting their time in doing an FPGA-based implementation, but scaling a design that's meant to fit onto a single chip to an FPGA, and it wouldn't be one FPGA, right? It would be dozens or even hundreds of FPGAs. That's also a non-trivial thing to do as well. And there's whole companies whose whole reason for existence is to provide that technology and to provide the glue logic to make that work in a fairly effective manner. Let me finish up this top. Well, no, let's not. Okay, I will briefly bring this up on Tuesday just to make sure we finish up this whole topic. You can also walk through it as well. The truth of it is, I guess, that I want you to understand viewing and the transformations that are part of viewing from the perspective of the hardware we're building, the shader core we're building. It's kind of a provided input output relationship, right? You're building a shader core whose job is to do math. And I'm telling you that the math it's doing is really important because it allows you to specify complex scenes and to transform and to position the camera and to do all these sort of things. But from the implementation perspective, from the role you have in this class, it's an input to your system, right? It's an input to your system and you're just doing the math. So I understand that I'm not feeling a huge energy level today, that it's hard to really care about, well, here's our orthographic matrix and here's what it winds up being, because from your perspective, for the way this class has been configured, it's just a matrix. It's just a matrix like any other, and we do need to care about the fact that it requires a division if we're doing a perspective versus if it's just in a parallel projection. We're starting to see, our assumptions starting to break as we implement more and more of our pipeline and get more and more realistic looking things working. So I still think this is important. I'll try to get through it and just jump back into shader architecture on Tuesday. So it's connecting more closely to what you've been working on in lab, starting on in lab on Wednesday. Otherwise, let's leave things here for today. Make a lot of good progress if you can on MP3 because there's a decent amount of work that needs to be done. It's not the it's not the same amount of VHDL as you had to do for MP2. The testing and debugging, hopefully you've learned some lessons because it is harder. There's more you have to test and debug in MP3, but for fewer number of lines of VHDL at the end of the day. We'll leave things here for today. Come to office hours if you're bored. I'll be around. But otherwise, I will see people on Tuesday.